Alright, so this is the lecture video for section 3.6. And in section 3.6, what we're going to look at are rational functions and their graphs. First off, like we said in the previous section, rational functions are simply just functions, or rationals are simply just things that you can write as a fraction. So therefore, rational functions are simply just functions that you can write as a fraction, where you have a fraction in the numerator. Here they're calling it p of x. And a fraction in the denominator, here they're calling it q of x. Where again, q of x can never be equal to 0, since we'd never divide by 0. And here it also says it cannot be equal to a constant, which means that here we're saying that this has to be some kind of function. It just can't be some number. Here we have a couple of definitions that we already know. Some here we're going to have a couple that are new. But first, we're going to say that the domain are simply just all real numbers, except for what make the denominator equal to 0. Here, removable discontinuities, or a lot easier way of saying that, are simply just wholes, are common factors both to both the numerator and the denominator. So the way to imagine this is if you have some function, but it's not smooth. Let's just say here at this spot right here, there's it's like an open circle. So for some reason, like this one spot is missing in this entire function. That's what we call a hole. Roots or intercepts, we already know that. Those are just the x values that make the numerator equal to 0. But they obviously cannot be a hole. Otherwise, the denominator would be equal to 0 then as well. The y-intercepts, that's just our constant term p of x divided by the constant term of q of x. Vertical asymptotes. So here, this is starting to be a little bit of stuff that we haven't really seen yet. Vertical asymptotes, those are going to be the x values that make the denominator equal to 0, but it cannot be a whole. So whatever makes our denominator equal to 0, but it's not a whole, that's what we're going to define to be our vertical asymptotes. So then, important thing to realize then is that if the numerator and the denominator have a common factor, that's what's a whole. If we can factor the denominator, but it doesn't have also the same factor in the numerator, then we're going to say that it's a vertical asymptote. For horizontal and slant asymptotes, we're going to look to see of the degree of the polynomial in our numerator and the degree of our polynomial in the denominator. If the degree of our polynomial in the denominator is larger than the degree of the polynomial in the numerator, then we're going to say that the horizontal asymptote is simply just y is equal to 0. If instead the degree of the polynomial in the numerator and denominator are equal, then the horizontal asymptote is simply just going to be the ratio of their leading coefficients. And for a slant asymptote, is only going to be the case if it's top-heavy, and when it's top-heavy, the degree of the polynomial in the numerator is larger than the degree of the polynomial in our denominator. Alright, so if all of that stuff so far was clear as mud, like I always say, don't worry about it. We're going to do a bunch of examples, and as long as it gets clear by the end, you'll be alright. So here we're trying to figure out whether these examples are top-heavy, bottom-heavy, or equal, and then we're also going to find their horizontal or their slant asymptote. So if we look at this first example right here, the degree of the polynomial in our numerator is just 1. That's the highest degree that we have there. But the degree of the polynomial in our denominator is 2, right? Since that's the highest exponent that we have there. So therefore, we're going to say that this one is bottom heavy, because we have a higher degree in our denominator. Well, if it's bottom heavy and we're trying to either find the horizontal or the slant asymptotes, if we come up here now, we can see that this right here, whenever it's bottom heavy, our horizontal asymptote is simply just, so I'm going to say that the horizontal asymptote, I'll abbreviate asymptote, is then just y is equal to 0. That's for the first one. Let's go on to the second one. The degree of our polynomial in the numerator is 2. The degree of our polynomial in the denominator is also 2. So therefore, we're going to say that these two things are neither bottom heavy nor top-heavy, but these two are equal. And if they're equal, then we're going to say that the horizontal asymptote is going to be y is equal to the ratio of their leading coefficients. So therefore, we're going to have a ratio, which again is just a fraction, of the leading coefficients. Well, the leading coefficient here is 5 because that's associated with our x variable that has the highest degree. And our leading coefficient down here is 3 for the exact same reason. So therefore, our horizontal asymptote is simply just going to be y is equal to 5/3. Let's go on to the next one. The degree of our polynomial in the numerator is just 1. That's the highest exponent that we have. The degree of our polynomial in the denominator is also just 1 because that's the highest exponent that we have on our x variable. So therefore, again, these are going to be equal. So just like we did before, if they're equal, then our horizontal asymptote is simply just going to be the ratio of the leading coefficients. So y is equal, we're going to have the ratio of the leading coefficients. Now the important thing to see here is the leading coefficient in our numerator is 8 because that's the coefficient that's associated with the x variable that has the highest degree. It's not 3. So it doesn't just mean the one that's out front, it means the one that's out front on the variable with the highest exponent. Here our leading coefficient is 2 for the exact same reason, so therefore here we're going to have that our horizontal asymptote is equal to 4. Now for our next one. The degree of our polynomial in our numerator is 2. The degree of our polynomial in the denominator is now 3. So again, here we have that we're bottom heavy. And again, if we're bottom heavy, as we have up here, it's going to say that our horizontal asymptote is simply just y is equal to 0. So the horizontal asymptote is simply just y is equal to 0. Now, lastly, if we go down to this h of x, the degree of our polynomial in the numerator is 2. The degree of our polynomial in the denominator is 1. So now we're top heavy because we have a higher degree in our numerator on top than we have in our denominator, which is on the bottom. So now when we're top heavy, now what we have is we have this thing called a slant asymptote. Slant asymptote happens whenever we're heavy. So whenever we have a slant asymptote, now we're going to say that y is going to be equal to the quotient of p of x divided by q of x. Well, you might be wondering, well, what is p of x divided by q of x? If we go up to our definition up top, this p of x is going to be what we have up here in our numerator, and q of x is going to be what we have down here in our denominator. And if we're finding the quotient of it, without the remainder, we literally have to divide these two things. That's what a quotient is. So that means that we literally have to divide these two things, right? Our numerator and our denominator. All right, so we have to divide these two things. How do we go about dividing this numerator by the denominator? Well, there's a couple different things that we can do. We can either do long division, or luckily in this case we can use synthetic division because we just have an x to the power of 1 right here. So if we can do synthetic division, let's do our synthetic division. We're going to take the coefficients of our polynomial in the numerator, so 2, 3, and 1, right? It doesn't skip any of the x terms, so I don't need a 0. I have this little symbol right here, and since this is x plus 5 right here, we're going to have minus 5 because we want to figure out what makes it equal to 0. Alright, so that's how we have the numbers, negative 5, 2, 3, and 1. Alright, how do we do synthetic division again? Again, we have this other horizontal line. We pull down the 2. Negative 5 times 2 is negative 10. Now we can add these two things, gives us negative 7. Negative 5 times negative 7 is 35. If we add these two things, we get 36. So we have a remainder. which means now a couple of things, right? It's a couple of things that's important to realize that here we have a remainder. This is our remainder term, which means that x plus 5 is not a factor of our numerator. Now, why is that important? That x plus 5 is not a factor of our numerator. Well, if we come back up here above to where we had our definition of wholes, we said that if they have a common factor, if the numerator and the denominator had a common factor, that's what we would consider to be a whole. And only after we take out these common factors can we find these asymptotes. So, since x minus 5 is not a common factor, it's not a whole. So therefore, what we can say then is, since we're top-heavy, we found the quotient. Let me scroll down a little bit more. Since we're top-heavy, we can find the quotient of these two things, and y is equal to that. It's then going to become our slant asymptote as long as we don't include the remainder. So let's take this answer right here. And what we would then have is we would have 2x minus 7 if we just forget about this remainder. Again, we're not looking at the remainder. So if we just have this term right here, 2x minus 7, that's going to be our answer to our slant asymptote. 2x minus 7 is going to be what we have right here without the remainder. All right. So that's the first page of notes. Let's go on to the second page of notes. And these next two pages of notes actually have quite a bit of work in them. So let's brace ourselves. All right. So we have a couple of examples here. We have 1, 2, and then it continues on the next page. It might actually, is there a second page after that? Oh gosh, it actually continues on the next page after that too. So we have 5 examples that we're going to go through. And these 5 examples that we're going to go through, for each of them, we're going to state all of this, right? So we're going to state the domain. We're going to state if there are any removable discontinuities or holes. We're going to state if state the y-intercept, state the x-intercept, vertical asymptotes, horizontal or slant asymptotes. We're going to sketch it, and then we're going to also state whether or not there's any symmetries here. So some of this stuff is stuff that we've already learned throughout the semester, or maybe you came to the semester already knowing it. Some of it is new to this page right here that we just got done going over. So I would recommend having this page handy. That way once we get to the stuff, like the vertical and horizontal and slant asymptotes, we can refer back to that. All right. Well, let's state first the domain. So let's start off with question A. If we want to state the domain, we know that the domain is simply just stuff that is not going to make our denominator equal to 0. So therefore, what we're trying to figure out is when is 3x minus 2 not equal to 0? Well, what we can do is we can figure out when it is equal to 0, and then make sure that x is simply just not that value. So if you solve for x right here, right, you're going to add 2 to both sides and divide by 3. We're going to say that x is going to be equal to 2/3. So x equal to 2/3 makes our denominator equal to 0. So therefore, it cannot be part of our domain. So therefore, our domain is going to go all the way from negative infinity all the way up to 2/3. But we're going to skip 2/3, and we're going to continue on to positive infinity. So now we have our domain written in interval notation. For part B, right, that's nothing new to this section. For part B, we're going to try to state removable discontinuities. Well, again, if we go over here to removable discontinuities or holes, we have to find common factors for both the numerator and the denominator. Do the numerator and denominator have a common factor? Nope, most certainly not. So here we have no common factor, so therefore we have no holes. Part C is asking us to state the y-intercept. How do we find the y-intercept? Well, we know that if you graph it, where's the y-intercept going to be? The y-intercept is going to be wherever x is equal to 0, right? Because here we have our y-axis. So if we want to find the y-intercept, we're just going to let x be equal to 0. We plug in 0 for all of this, we're going to have 0 minus 4 divided by 3 times 0 minus 2, which is just the same thing as minus 4 divided by minus 2, which is just positive 2. So therefore, our y-intercept is going to be at x is equal to 0, y is equal to 2. That's not new to this section. Part D, state the x-intercepts. So for our x-intercepts, what do? If we want to find the x-intercepts, we're going to set y is equal to 0. So since this is a function, we can just restate that as, right, y is equal to f of x. So we can say that 0 is equal to x minus 4 divided by 3x minus 2. So we let f of x be equal to 0, which is the same thing as y is equal to 0. Now we're going to try to solve for x. So if we try to solve for x, first thing that we're going to do is we're going to multiply both sides by this denominator, 3x minus 2. If we multiply both sides by the denominator, we're going to have 0 times 3x minus 2, which is still just 0. And if we multiply the right-hand side now by 3x minus 2, well, we can get rid of our denominator, so we just have this. So I've multiplied both sides by 3x minus 2. Now if we're still trying to solve for x, I think we're all good with the fact that x is equal to 4. So our x-intercept is going to happen at x is equal to 4. So therefore our x-intercept is 4, 0. Alright, let's go on to E. The vertical asymptotes. Oh gosh, our vertical asymptotes. So let's try to figure out how we figure out our vertical asymptotes. Well, if we want to figure out what our vertical asymptotes are, that is new to this section. So we can go back to this sheet right here. And it tells us how to find our vertical asymptotes. It says the x values that make the denominator equal to 0 as long as it's not a whole. Right? Well, we don't have any holes in this problem. So we just have to figure out the x value that makes our denominator equal to 0, right? We already said we have no holes. So we just have to figure out which value makes our denominator equal to 0. Well, we already did that. We already said that here, for our domain, we identified where our denominator would be equal to 0. So therefore, x is equal to 2/3 is our vertical asymptote, because it does not make our because it makes our denominator equal to 0 and it's not a whole. So this right here is our vertical asymptote. Alright, F. State the horizontal or slant asymptotes. Alright, so if we want to figure out the horizontal or slant asymptotes, that's what we did a lot on the previous page. And for horizontal or slant asymptotes, we have to see if we're bottom heavy, equal, or top heavy. That's what we did on the previous page. So let's see here. The highest exponent in our numerator is 1. The highest exponent in our denominator is equal to 1. So therefore here we're equal. And if we're equal, we said that the horizontal asymptote is going to be the ratio of our leading coefficients. So therefore here we're going to have a horizontal asymptote, which is going to be the ratio of our leading coefficients. And our leading coefficient in the numerator is just 1, and the leading coefficient in our denominator is 3. So here we have our horizontal asymptote. Alright, golly, now we're gonna graph this thing. Alright. So here luckily we're just sketching it, right? It even says if you wanted to have a more accurate sketch, find some more ordered pairs. But let's try to go through this right here. We know that part D, we had our x-intercept, so it's going to happen at 4. We go 1, 2, 3, 4. So here we're going to cross the x-axis. Our vertical asymptote happened at 2, so here we're going to go up 0, 1, 2. So we're going to cross the y-axis right there. We have a horizontal asymptote as y is equal to 1/3. So y is equal to 1/3. We're going to have a horizontal asymptote. Now, we haven't really talked in length about what the definition was of an asymptote. So let me backtrack here for a second and talk about what an asymptote is. Because usually the concept of an asymptote is misunderstood by a lot of people. An asymptote, if I represent this asymptote by simply just this dotted line, usually what people think is that an asymptote is something that you get closer and closer and closer to, but you never cross it or touch it, right? So you just keep on getting closer and closer and closer and closer and closer, but you never cross and touch it. And technically, that definition for an asymptote is incomplete, because it's true the fact that for an asymptote, a function is going to keep getting closer and closer and closer and never touch it or cross it. But that just means that after a certain point, right? After a certain point, you're going to keep getting closer and closer and closer and never touch it or cross it. But what happens before that point is ambiguous, which means that we most certainly can cross this asymptote, but after a certain point, we keep on getting closer and closer and closer and never touch it. That's what we're going to call to be an asymptote. So here, I just happen to draw this line horizontally, so this would be a horizontal asymptote. If we did the same thing just in reverse, right, if we made it a vertical dashed line instead, now we're just talking about vertical asymptotes. So here for this example, usually, and especially in this class, we very rarely see functions that you cross a bunch of times before it becomes asymptotic. But just remember that we can see that, but it's just going to happen rarely. Usually the examples in this class are going to be super straightforward. So here we're going to have a vertical asymptote of 1/3. Let's see, what else do we know? And then we know that we're going to have a hole at 2/3. All right. If we wanted to go through and sketch this, I'm going to spare you guys this a little bit, but it's going to look something. It's going to look something like this right here. Right, and this is just supposed to be a sketch, so it's going to look something like that right there. Again, if you want to get something a little bit more accurate, a little bit more precise, you can punch that stuff into your calculator. But we'll call this up here, we'll call this G. That's going to be our sketch. All right, and then H, state if there is any symmetry about the y-axis, x-axis, or the origin. And here, if we look at this, right, you can't spin it around the y-axis and get the same image. You can't spin it around the x-axis and get the same image. And you can't spin it around the origin and get the same image. So therefore, we're going to say that this has no symmetry. So no, not about x, y axis. So I'm going to say this is the x-axis, the y-axis, or the origin. That's not where we have symmetry. All right, so that's number 1. We're going to go through the exact same thing now for the next couple of examples. So let's do it. And again, if you want to pause the video and try this by yourself, or if you get fed up with all the examples that we're about to do and you don't want to watch the entire video, that's completely fine. But I'm just going to go through this at a more brisk pace. I'm still going to talk my way through it. But if you ever need to slow down, you can pause and rewind, or pause it now and try these things by yourself. All right. So for A, we're trying to figure out our domain. So we want to figure out where our denominator would be equal to 0, and we're just going to leave those numbers out. So we're looking to see what values we can plug in for x that would make our denominator equal to 0. So what we're really looking for are two numbers that add to positive 1 but multiply to negative 6. So that means that at x is equal to 3 and negative 2, this is where, this is how we can factor it. So therefore, when x is equal to negative 3 and x is equal to positive 2, that's where our denominator is equal to 0. So therefore, our domain is going to go from negative infinity all the way up to negative 3. We're going to jump negative 3 and go up to positive 2. Then we're going to jump positive 2, and we're going to go on to positive infinity. So here's our domain in interval notation. For B now, we want to figure out whether or not there are common factors in the numerator and the denominator for our wholes. So again, if it's a whole, if there's a whole, then the numerator and the denominator have to have a common factor. So the question is now, we already factored our denominator, which is what we have right here. Can we factor our numerator? Well, x squared minus 4 is something that we can factor. We can factor it to x plus 2 times x minus 2. Which means that if I can rewrite this over here, our numerator we can write as x plus 2 times x minus 2. And our denominator is what we can write as x plus 3 times x minus 2. So therefore, we have a common factor in our numerator and our denominator. The common factor is x minus 2. So because x minus 2 is a common factor, wherever this would be equal to 0, so at x is equal to 2, that's going to be our whole. Right? So again, if we have a common factor in our numerator and our denominator, what would make that common factor equal to 0? So here our common factor is x minus 2. What would make all of this equal to 2 is if x was equal to 2. So therefore, x is equal to 2. That's where we're going to have a whole. All right, let's go on to part C. C is asking us to state the y-intercept. So wherever we want to find the y-intercept, we're going to let x be equal to 0. So we're going to have 0 squared minus 4 divided by 0 squared plus 0 minus 6, which is negative 4 divided by negative 6, or positive 2/3. So therefore, our y-intercept is going to be at 0, 2/3. D is asking us to find the x-intercept. So again, if we want to find the x-intercept, we're going to let y be equal to 0. So we have this right here, x squared minus 4 divided by x squared plus x minus 6. Well, the first thing that we can do, just like we did before, is multiply both sides by the denominator, which is going to give us 0 is equal to x squared minus 4. Now, if you're asking to figure out, hey, what values can I plug in for x for this to be equal to 0? Well, here, right, if you have this minus 4, right, then we know that x can be equal to plus or minus 2. So plus or minus 2 then are going to be our x-intercepts, right? At plus or minus 2, that's where we would intercept our x-axis. But keep in mind here that 2 is not in our domain. 2 is not in our domain, and 2 is also that whole. So therefore, we would have touched the x-axis at 2, but we're really only going to touch the x-axis at x is equal to negative 2. But if we could plug in the value x is equal to 2, then that would also be where we would intersect our x-axis. But here the answer is just our x-intercept is at x is equal to negative 2. All right, D, then E, state the vertical asymptotes. Say the vertical asymptotes, if any. Well, we want to figure out what makes our denominator equal to 0 and is not a whole, right? That's for our vertical asymptotes. X values that make our denominator equal to 0 but is not a whole. So what makes our denominator equal to 0 that's not a whole? Well, we know that these two values make our denominator equal to 0. 2 is a whole. So therefore, the value that makes our denominator equal to 0 but is not a whole is simply just x is equal to negative 3. So when x is equal to negative 3, our denominator is equal to 0, and x is equal to negative 3 is also not a whole. All right, F. State the horizontal and the slant asymptotes. So for horizontal and slant asymptotes, we're going to see if we're bottom heavy, top heavy, or neither, right? The bottom, horizontal and slope, bottom heavy, equal, or top heavy. Our degree of our polynomial here is 2. Degree of our polynomial denominator is also 2. So therefore here we're equal. And when we're equal, or horizontal asymptotes is going to be the ratio of the leading coefficients. So our leading coefficient up here is simply just 1. And our leading coefficient down here is also 1. So therefore y is equal to 1 is going to be our horizontal asymptote. Alright, now lastly for, well, G, I guess, G, we're going to try to sketch this thing again. So let's see what we have. We have a couple different things right here, but basically what we have is we have our y-intercept at 2/3. So I'll call this one right here 1. So right here, this is going to be our y-intercept. Our x-intercept is at x is equal to -2. So we're going to be down here. And we have a horizontal asymptote as y is equal to 1. So here we're going to have some kind of horizontal asymptote. Do we have a vertical asymptote? Yeah, we have a vertical asymptote at x is equal to -3. So here we're going to have a vertical asymptote. Now this g is suddenly in the way. Get rid of this g right here. Alright, so here this is -1, this is -2, and here we have -3, which is our vertical asymptote. And then we have a hole at x is equal to 2. Gosh, there's a lot of stuff in here. Alright, so we still have to be below this vertical asymptote, so here we're going to have this hole. So we can see that we're going to go right here, we're going to skip this point, we're going to cross the y-axis right here, and then we're crossing the x-axis right here, and then this is an asymptote. Now, if you go out and you graph this for other x values and y values, we're going to see that this graph continues over here like this. So here's a sketch of our graph. Then if we look at this, it's definitely not symmetric about the y-axis, right? You can't spin this thing around the y-axis and get the exact same figure. You can't spin it around the x-axis and get the same figure. And you can't spin it around the origin. So again, we're going to say that it's not symmetric about the x, the y, or the origin. So this is the x or y axis, or the origin. Alright, that's example number 2. Let's move on to example number 3. So for example number 3, we're going to go through that exact same process. So for A, we're going to try to figure out what makes our denominator equal to 0. And again, we want to figure out what's going to make, whether or not we can factor this. And what we can see is that we actually can factor this because we're looking for two numbers that add to -3 but multiply to -4. So it's going to be -4 and +1. So that means that we can go from -infinity to -1, union that with -1 to +4, union that with 4 all the way up to +infinity, right? Because we factored our denominator and we figured out what values are going to make our denominator equal to 0. For B, we also want to figure out if we have any common factors in our numerator, and in fact we do, right? So let me rewrite this here. We have this as and here I can rewrite this as 2 times x minus 4. I can pull a 2 out of both those things. So the x minus 4 are the factors that we have in common. So the common factor is x minus 4. So therefore, the whole is that what's going to make this equal to 0, and what's going to make this equal to 0 is when x is equal to 4. Now for C, we're asked to find the y-intercept. We're going to find the y-intercept whenever we let x be equal to 0. So we're going to have -8 divided by -4, which is just the same thing as 2. So therefore, our y-intercept is at 0, 2. D is the x-intercept. That's when we let y be equal to 0. Just like we always do, we're going to multiply both sides by the denominator, which leaves us with this. Solving for x, if we add 8 to both sides and divide by 2, we're going to have x is equal to 4. So therefore, we would, our x-intercept would be at x is equal to 4. But now remember that x is equal to 4 is also our whole, so x cannot be equal to 4. So therefore, we have no x-intercept. No x-intercept, because this is where the x-intercept would happen, but the x-intercept at x is equal to 4 isn't part of it, so again, we're not going to intercept our x-axis. Here, then E, we're looking for the vertical asymptotes, and again, for the vertical asymptotes, we're going to see which degree of the polynomial is greater in the numerator and in the denominator. Well, here the denominator, so we're definitely bottom heavy. And if we're bottom heavy, then our horizontal asymptote is simply just y is equal to 0. All right. That's E for bottom heavy. For F, did I skip one here? We stated the vertical asymptote. Oh, I did this a little bit backwards. I got that messed up, y'all. So I was talking about finding the horizontal and the slant asymptotes, and I was calling it vertical asymptotes in that example. So what this really is right here is I just found that our horizontal asymptote, but for some reason I was writing horizontal, but I think I was saying vertical, because for E I was supposed to find the vertical asymptote. But for vertical asymptotes, we don't look to see which one of these degrees is larger. For the vertical asymptotes, we're looking to see what makes our denominator equal to 0. So I think I might have been saying, and it's getting late, right? I think I might have been saying that I was finding the vertical asymptotes, but I was writing horizontal asymptotes all along. So for the vertical asymptotes, I want to figure out what makes my denominator equal to 0, but is not a whole. So therefore, the thing that makes my denominator 0, but is not a whole, is when x is equal to -1. And if x is equal to -1, that's when my denominator is equal to 0, but it's not a whole, because we already said that x is equal to 4 is a whole because it's a common factor. So I'm going to write vertical asymptote. So I think I was calling the horizontal asymptote the vertical asymptote. Just in this example, right? This is the one I was messing it up in. 1 and 2, I was good to go unless I just didn't catch it. All right, then we're going to graph this thing again. So let's try to graph it. We have our whole at x is equal to 4. So we're going to have a whole at x is equal to 4. We have a y-intercept at 0, 2. So we're going to cross the y-axis right here. We don't have an x-intercept, because we would have had it at x is equal to 4. And then we have a vertical asymptote at x is equal to -1. So here we have a vertical asymptote. And we have a horizontal asymptote at y is equal to 0. So our x-axis, that's going to be our horizontal asymptote. So what we're going to do then is we should look something like this. And then we meet all of those criteria. So now if we look at h, again, we can't spin it around the y-axis and end up with the same thing. We can't spin around the x-axis and end up with the same thing. We can't spin around the origin and end up with the same thing. So therefore, we're going to say that it's not symmetric about the x-axis, y-axis, or the origin. Right. See if I can get through number 4 without messing up E and F again. Alright, so first things first. For part A, we're trying to state the domain. The domain is simply just going to be every x value where our denominator is not equal to 0. And here the only thing that makes our denominator equal to 0 is when x is equal to 1. So we can go from negative infinity to 1, skip 1, and then go all the way up to positive infinity. For B, we're trying to find any removable wholes or discontinuities. So we want to see if there is a common factor in the numerator and the denominator. So there's now a couple different ways that we can find common factors, or just factor stuff. And if we factor the numerator, what we're actually going to end up with is x plus 2 times 2x minus 1. There's a couple different ways that we can go about and find those factors, but for now we'll let it suffice, since that's something that's prior to this section, something that we should already know how to factor these things. We'll just leave it as that. But for B, since we're trying to find any removable wholes or discontinuities, since we have no common factors, we also have no holes. For C, we're trying to state the y-intercept, and whenever we're trying to find the y-intercept, we let x be equal to 0. If we let x be equal to 0, we're going to plug in 0 here, 0 here, so it's going to be negative 2 divided by negative 1, which is just equal to 2. So therefore, at 0, 2 is where we have our y-intercept. For D, we're going to try to find our x-intercept. That's where we let y be equal to 0. So again, we would have this all equal to 0. We always multiplied our denominator by both sides. So therefore, we just have this right here equal to 0. Well, when does this equal 0? Well, according to what we have up here, if we plugged in x is equal to negative 2, that would be equal to 0. And if we plugged in 1/2, and we plugged in 1/2, then 2 times 1/2 is 1, and 1 minus 1 is equal to 0. So if we plugged in 1/2, that's where these two things would be equal to 0. So that's going to also be where our x-intercepts are. So our x-intercept is then going to be at negative 2, 0, and at 1/2, 0. Those are our x-intercepts. All right. Now is where we're getting to the point where I messed up before, so let me make sure that I'm saying it right this time. In E, we're going to find our vertical asymptotes. All right, in E, we're finding our vertical asymptotes. Now, for vertical asymptotes, we want to figure out what makes our denominator equal to 0, and it's not a whole. So what makes our denominator equal to 0 and it's not a whole? Well, we have no holes. So therefore, everything that makes our denominator equal to 0 is going to be a vertical asymptote. So therefore, what makes our denominator equal to 0? Well, x is equal to 1 makes our denominator equal to 0. So therefore, x is equal to 1 is our vertical asymptote. All right, I think I got it right that time. Because now we're going to go on to F, and F is asking us for horizontal or slant asymptotes. So for horizontal and slant asymptotes, we're going to compare the degree of the polynomial in our numerator to that of the denominator. Here I think we'll all agree now that we're top heavy. And if we're top heavy, we see that we're going to have a slant asymptote. And for a slant asymptote, we actually have to find this quotient. So therefore, here we're going to have a slant. And the way that we're going to figure out what our slant asymptote is by actually taking this quotient, by dividing these two things, and then not considering our remainder term. So, let's do it. We want to divide these two polynomials. We can use synthetic division again, since here our x just has the highest degree is just 1. So therefore we're going to have 2, 3, and negative 2. Again, I don't have any zeros because I'm not skipping any terms. And over here I'm going to have a positive 1, since that's what makes our denominator equal to 0. Pull down the 2. 2 times 1 is 2. Add these two things. 1 times 5 is 5. Add these two things and we get 3. Again, this 3 right here, this is our remainder term. So therefore, if we don't consider our remainder term, this is going to become our constant term, and this is going to become our x term. So we have 2x plus 5. Again, I'm writing it without the remainder. So therefore, now this becomes our slant asymptote. And a slant asymptote, some of you might be thinking what a slant asymptote is. That's not something that I've articulated yet. Horizontal, I think everybody's good with the fact that a horizontal asymptote, that's horizontal. A vertical asymptote, well, that's vertical. Well, a slant asymptote is simply just an asymptote that's neither horizontal or vertical. So therefore, you can see right here, this is just some kind of straight line with a positive slope. So a slant asymptote is simply just an asymptote that's neither horizontal or vertical. All right, so that's F. G, all right, let's take a look at G. G is going to be a tough one because we have this slant asymptote thing going on. But let's draw our x and our y-axis. All right, so for whenever we let x be equal to 0, here we have our y-intercept at 0, 2, so 1, 2 here. This is where we're going to cross the y-axis. We're going to cross the x-axis at negative 2, so negative 1, negative 2. We're going to cross it right here and at 1/2. So we're going to say this right here is 1. Here we'll get 1/2. So here, negative 2, positive 2. That's 1/2 right there. I'm going to cross the x-axis right there. And we also have a vertical asymptote at x is equal to 1, so we have this vertical asymptote that comes right here. And now we have some slant asymptote, and this slant asymptote is going to be 2x plus 5. So we're going to cross the y-axis at 5, 2, 3, 4, 5. And we have a positive slope, so it's going to look something like this, right? Here's our slant asymptote, looks something like this. And it's just a sketch, right? All right, now we need to connect these dots. So let's see how we connect these dots. The way that we're going to connect these dots is actually going to look something like this. And then over here, this continues. Here, it's going to look something like this. So we have these two portions on our graph. And again, if you're wondering how I'm getting this, you can just plug in additional x values in right here. It'll spit out y values, and you can go ahead and graph this graph. So here's a sketch of the graph. Then for H, it's asking us, is this symmetric about the y? No, definitely not. You can't spin it around the y and get the same thing. Symmetric about the x? Definitely not. You can't spin around the x and get the same thing. Symmetric about the origin? Nope. So not about the x, y, or origin. So it's not symmetric about the x, y, or the origin. So far we've had none of them are symmetric about the x, y, or the origin. Right, so that's number 4. Let's go on to the last example. I know this is turning into quite the ordeal here. I'm trying to go through it slowly since we're not in class and you guys don't have the opportunity to ask questions. Hopefully, if you're good with this stuff, like I said before, just go ahead and stop the video. You don't have to watch all this stuff or skip to the end or whatever. But we're still going to do this one. All right. Part A is asking us to state the domain. What makes our denominator equal to 0? Well, either positive 5 or negative 5 is going to make our denominator equal to 0. So here, this is actually going to factor out to x plus 5, x minus 5. So positive 5 or negative 5 would make our denominator equal to 0. So we're going to go from negative infinity up to negative 5, union that with negative 5 to 5. And and then union that with 5 all the way up to positive infinity. For part B, we're going to try to see if we have state any removable discontinuities, or these are simply just holes. Again, for removable discontinuities, we have to find common factors. You might be asking yourself, well, what are our factors of this numerator? Our factors of this numerator are going to be 2x minus 1 times x minus 5. This should be a minus. So do we have common factors? Well, we sure do. It's x minus 5. So therefore, we have a whole at x is equal to 5. Since that's our common factor, and x is equal to 5 would make our common factor equal to 0. State the y-intercepts. This is going to be equal to 5 over negative 25 or negative 1/5. So 0 comma negative 1/5. D is going to ask us for the x-intercepts. So we're going to have this again. We already said that what makes this equal 0, right? Again, technically speaking, it's this. Since we're setting y equals 0, multiply both sides by the denominator. Now we just have to set our numerator equal to 0. What values of x make our numerator equal to 0? Well, we already said that these two things factor to 2x minus 1 and x minus 5. So therefore, here x is going to be equal to 5, and x is again going to be equal to 1/2, since we can plug in 1/2 right there, and that would be equal to 0. So therefore, our our x-intercepts are at 5, 0, and at 1/2, 0. That's for D. For E, okay, let me make sure I get this E one right again. We're going to state the vertical asymptotes. For vertical asymptotes, we want to find out which x values make our denominator equal to 0, but these aren't wholes. We have a whole at 5, so therefore, what's going to make our denominator equal to 0 that's not 5? Well, that's negative 5. So therefore, here, we're going to have x be equal to negative 5. That makes our denominator equal to 0, but is not a whole, right? So therefore, we're going to have x equal to 5. F, we're going to try to find the horizontal or slant asymptotes. That's where we compare the degree of the polynomial in the numerator to that in the denominator. Here we have that it's 2. Here we have that it's 2. So we're equal. And whenever we're equal, our horizontal asymptote is going to be the ratio of our leading coefficients. So we're going to have a horizontal asymptote, which is the ratio of our leading coefficients. In our numerator, it's 2. In our denominator, it's 1. So therefore, y is equal to 2 is our horizontal asymptote. It's asking us to graph these things now. So here, let's do it. We have our y-intercept at 0, negative 1/5. So here I'm going to call this negative 1. So negative 1/5 is going to be somewhere like right here. Our x-intercepts where are x-intercepts? 5, 0, and 1/2, 0. Oh, I saw here I missed something then, right, when I said this. Here we have a whole at x is equal to 5, so therefore this right here, we never reached that point. So therefore this right here is not an x-intercept. We only have one x-intercept, which is that x is equal to 1/2. So when x is equal to 1/2, here it looks something like this spot right here. We have a horizontal asymptote as y is equal to 2. So here, this is 2, so we have a horizontal up here. And our vertical asymptote is when x is equal to negative 5. Golly, so all the way down here at negative 5, we have some kind of vertical asymptote. So once again, this g is getting in the way. never seem to find a good spot for this g. Alright, now if we look at this, getting myself a little cramped here, but it's going to look something like this. Keep on approaching it that way and this way, and up here we're going to have it up. Definitely got cut off up there, but you can think of it as just being some kind of sloped line that goes in between these two asymptotes. Alright, now for h, saying is it symmetric about the x? Can we spin around the x? Nope. Can we spin around the y? Nope. Can we spin around the origin? Nope. So again, for all of these, then we had that it's not symmetric about the x-axis, y-axis, or the origin. So that's the same answer that we had for all of these. Alright, now the next couple of problems are practice problems, and that stays for you, so that then concludes the lecture video for 3.6.